So this is something we're working at Cordesa. We believe that we are creating, or we are somehow pushing a new discipline that we like to call it computational corrosion analysis. And this is something that has taken a really nice shape, of course, because of the partnership and the help of Siemens, absolutely. The way we see corrosion, or computational, or CFD for corrosion applications, is, I would say, a little bit different than the rest, because sometimes we think about multiphysics simulations and we see stress analysis, thermal fluid guys working together. They do fantastic things, multi-projective optimization, all of that, and they come up with these nice geometries, thicknesses that work pretty well from the thermal performance standpoint, stress perfectly fine. But all of a sudden, when they bring the part or design to manufacturing and it's actually working, they realize that, wow, we have an issue. And the issue is corrosion. And that's the story. That's actually something that happened really, really common in industry. And that is why we want to push the envelope. We want to help our customers to resolve the problem they're going to have 5, 10 years early in the design process. The reason is simple. It's just because corrosion is expensive. Unfortunately, that's the truth. It's really expensive, in addition to how ugly these bolts look when they're rust. It's actually really expensive. So here we have two different airplanes, and not because I'm showing airplanes, it's just a problem from aerospace. It is actually a problem we see everywhere. Marine applications, biomedical applications, aerospace applications, automotive, it's everywhere. So here it's clear that this is definitely a lot newer airplane compared to this one over here. And maybe we have 50 or 60 years apart from each of these two designs, but still we are seeing problems, errors in the design process. So this one is pretty much $300 million to resolve the problem here in the gap filler, where Cordesa was part of the team, or we helped them to identify and mitigate that. Actually was an incompatibility of the material, but it was a really expensive mistake. And on the other hand, here we see 20 billions. That's basically what it takes to repair the C-17, if I'm not mistaken. Corrosion is definitely complex. It's really, really complex because we have so many different mechanisms here. We have galvanic corrosion, of course. We have pitting corrosion, we have crevice, we have so many different mechanisms. And the reason of the complexity is not because of the different mechanisms, but also because of the type of different things that are actually taking place while we have corrosion. But not because of the complexity of the problem, we should stay away from modeling, because there are other areas like turbulence, for example, combustion, chemical reaction, that are as complex as corrosion, but we are seeing that folks are doing really good progress in those areas. But we at Cordesa, we still see that corrosion is still in the Stone Age. So we have really fast computer, we have really efficient numerical methods, but still we don't see the community embracing CFD applications, or even not even CFD, applications that we have developed to mitigate corrosion risk. And more importantly, 80% of all these problems are related to galvanic corrosion. So if we focused on that 80%, we're going to make a really, really positive impact in the industry. Not only in the industry, but of course in other areas as well. This is how we used to tackle corrosion problem. This is actually called the galvanic series, and this is based on thermodynamics. Okay, basically what we see here is noble materials and less noble materials. And basically what this table says, and that's what we have been using for the last 60 or 70 years, is that the further they are apart, the more corrosion we're going to see. So if, for example, just to make the example here, these two materials will definitely show lower corrosion than, for example, zinc and copper over here, because they are really far apart from each other. But you can really see that these become really complicated once you start working with complex systems, with multiple material, multiple phase pairs, and all of that. The mill standard is what the DoD is now using. They said now it is time for us to come up with, or to use a standard so that everybody, OEMs, can use a common ground. And this is really simple to use. A table, as we see here, we have this column over here with some materials, another column here that actually represents the same material. So for example, 11 is 11 over here. So if we want to determine the corrosion rate between steel and this stainless steel over here, it is basically just about crossing or drawing a line with 11 and intercepting that with the 30. And that basically says that the corrosion risk is number 3, and that says that we are going to have a corrosion rate around between 1 and 5 mils per year. This is a method that is now used in the DoD, the Department of Defense is using that, but it has a main limitation. And the limitation is that we have to use this with 1-to-1 anode cathode ratio. Once we change the anode cathode ratio, this doesn't work anymore. We cannot use that anymore. And it's clear that actual systems, they don't have that. We don't have that 1-to-1 cathode ratio. Another issue is that imagine now you have multiple materials, and now you have to start keeping track of the combination or the interaction of this material with the one at the bottom, the fastener with this one, the fastener with the other one. And you can quickly see that that becomes really complicated. Really, really complicated, really cumbersome. And of course, the material database is limited. And most of the time, companies like Northrop Grumman, General Dynamics, you name it, Lockheed Martin, they develop their own recipes, their own material, and they want to know what is the electrochemical signal of their material so that they can understand their system better. Because of that, Cordesa, we developed, I think it was 7 years ago, our product called Corrosion Gene. And Corrosion Gene is not only a software that provides you information about the corrosion rate, it is also a database management system, which means that you can actually, Lockheed Martin can, hey, I need you to add this material that I created for this system in my database. Okay, perfect. Give us the material, we run the test, and we're going to update the database for you for Corrosion Gene. Another important feature that we have in this version of Corrosion Gene, that now we can work with different anode cathode ratio, which is extremely important. You will see that shortly. And now we are working in another application, another feature, excuse me, that considers the different film thickness. So we can see the role that the thickness play in the corrosion rate. Thinner thickness, of course, increases the corrosion rate, and thicker film thickness basically reduces the corrosion rate. And also we have different chemistries here. We have, of course, the one from mill standard and the 3.5 sodium chloride. This is exactly the same example I showed a few minutes ago about the mill standard. Exactly the same. So we have 1020, I think, yes, 1020 and 304. But we clearly see that this is a lot different from what we have in the table. However, this is exactly the same what the table has or what the table represents. But we use the kinetics, the actual kinetics. And kinetics is extremely important here because depending on the film thickness, this branch over here, the cathodic branch, changes. It either shifts to the right or to the left. Therefore, it's really important. Similarly with the anode cathode ratio. We're going to see that in a minute. So from Corrosion Gene, once we run this, which takes a few seconds, it's actually really fast, we have information that is important for our electrochemical team. We have OCP, we have self-corrosion rate, we have all that information. But more importantly, we see that we get the same risk rating, the mill standard rating, excuse me. In this case, it's number 3, and if I quickly go back, you can see that that was exactly the same number we have here. We use the same procedure in the back end called mixed potential. That's what we use. In this slide, we see the role of the anode cathode ratio. Anode cathode ratio 1, again, 3, and we have somewhere 2.2 mils per year. And by increasing the anode cathode ratio, we now have 5. This is not captured by the mill standard. Even though we use the same mixed potential, even though we use the same physics in the back end, the standard doesn't capture that, whereas corrosion gene does. The question is, how can we use that for real systems? Because for one-to-one anode cathode ratio, or even for different anode cathode ratio, we have a solution. But for real systems, it is evident that using polarization curves is way too complicated. Because now we have to see what happened with this curve over here, or the interaction between this curve, and all of them. And this is actually what we used to do in the past. Using the mill standard is pretty much impossible, because I just demonstrated that the anode cathode ratio is important. That's the reason why we focused on the development of computational frameworks based on a robust and a sound formulation, which is the mixed potential, that has been widely validated. And that's really important, because that's what we say. Our database has been widely validated, and it's exactly the same procedure that a mill standard has or uses in the NID. That is why we said, okay, if we understand that data is important, no matter where we use it, how can we leverage that in different stages of the engineering process, starting from the far left all the way to the far right? Remember, now this is mandatory, mill standard. And what is even more important, that this standard over here, the 1568, says that modeling and tests shall be used. And that is important because if other areas of engineering are using modeling for certification, like FAA is actually considering CFD for certification, why the corrosion space are still using tables and Excel sheets? That doesn't really make sense. That's the reason why we said, okay, let's just make our very best to use the data that is accurate to resolve complex systems, and let's just create multiple solutions. Because we don't believe that one size fits all. We don't believe on that. Again, we have, at early stage of the project, we can use for conceptualization tasks, for example. We can definitely use corrosion gene, no problem. Well, we know we are going to have this component, has this material, we have this area anode cathode ratio. Okay, corrosion rate will be somewhere around here. That's perfectly fine. We can work with that. It will definitely help to avoid problems that we see in the C17 and the I think that was the F35. I usually confuse the 22 with the F35. But it's clear that now we have a tool that we can use. Okay, but systems are complex. Well, no problem, we got you. Siemens and Cordesa, we joined efforts together and we pushed our database into NX. Now that solution is integrating in NX. And you will see shortly how a simple click will basically interrogate the entire CAD, and it will tell you, hey, watch out, you're going to have an issue here. Hey, you are here, you are good here, go ahead. And this is important because what usually happens is we can start resolving galvanic issues here. Remember, 80% of the problems are galvanic corrosion. So if we can start resolving problems once the design, once the engineering team has defined different sections or have locked in a few aspects of the design, we can actually bring all these here, and we're going to help the engineering project in a really positive way. The other way, the one I enjoy the most, is CFD, because I'm a CFD guy. Here I want to quickly mention a few important aspects of the CFD workflow. Most of the time, when we think about CFD, we think about turbulence and combustion and multi-phase flows, all of that. And one thing that I particularly like about the solution is that the equation we are solving is the potential of the, is the Laplacian, excuse me, of the potential field, which has an analytical solution. And that's the equation we solve. So we don't solve the flow, we don't solve, for example, we don't use either simple or piso, whatever, or any of these two algorithms. We just solve the potential, the Laplacian of the potential field, which means that even though the mesh seems really fine, because we had to refine the mesh for multiple reasons, it's really fast. You can run these problems really, really fast. And on top of that, remember that garbage in, garbage out. Well, assuming that we reduce the numerical errors because of the mesh, procedure, the solver, all of that, if I use a boundary condition that is exact by nature, it means that at least my solution will be exact, assuming that my numerical error is really low. And that's something that we believe we are providing to our customers, because we're using this boundary condition into my CFD. And theoretically speaking, this has or accept analytical solution. Anyway, coming back to this, sustainment. Once we do our very best resolving all the problems here, and even over here, we still have folks that are dealing with things that were designed and developed 50, 60 years ago, and they need to resolve their problems. And we cannot say, oh, you know what? We can't, because we just focus on the design, or we can just resolve the problems at this stage. No, we can't. And actually, we do. One of our main customers is the Air Force that, again, thanks to Siemens and our partnership, we developed something that we call the Corrosion Toolset that you are going to see in a minute. So in summary, we use the same data to all these different type of solutions. Of course, this takes seconds, 1 minute, weeks and days, and minutes, as you will see. This is a quick demo I'm going to share with you with the next. Again, we see the same section here. Now, after bringing that here into an X, again, the mindset here is, let's just focus on those complex sections. Let me just define those areas where we have high corrosion risk, and let's try to resolve them in an X. Here we have, for example, 29 parts have 4130. So imagine, for example, doing this with the table or the polarization curve. That will be too much work. Look here, so this is an X. I'm pretty sure you all are familiar with this. Now the feature is actually in the production version of an X. I brought the section, the part, excuse me. I will select the whole thing because I want to check my corrosion risk, 238. Click. It's actually going through all the body pairs. We have all my body pairs here. But remember, we have to go to the phase pairs because one body can have multiple phase pairs or interact with multiple materials. That's what I'm doing here. And I have my galvanic corrosion. And now I see that all of red is good, then yellow and red. As simple as that. We basically reduce weeks or days of work in seconds. And of course, I cut a few sections of the video, but that didn't take more than a minute. So the idea here is, let's be proactive. It is not enough to, oh, we have corrosion, to predict. No, we have to predict, mitigate, prevent, of course, and manage. Now let's solve the problem. Let me, for example, solve that section over here that we see that we have a corrosion rate somewhere around 230. That's aluminum 6013. And I'm changing that to aluminum 2024 because I have to be consistent. Yeah, I had aluminum at the beginning. Let me just change that aluminum for a different series. In this case, it's 2024. And what you're going to see is that now I resolve my issue from 4, the corrosion risk was 4, now it's 2. We solved the problem. So what if we use these way early in the process and we leave those really complicated parts or those complicated subsystems to the experts? Because definitely this doesn't mean that we are not going to have issues with corrosion. This means that we can solve a lot of the problems that are difficult to track once you have this complex system. Remember, we have teams of people working on multiple different areas, and most of these issues are actually picked up really late in the process, and at the end it's just too late. You have to work with coatings and all of that. So the idea is to, okay, let's start with the good material selections from the get-go. Now you're going to see how CFD complements the tool set here. Again, so we have this component. Initially, we just analyze the interaction between this piece over here and this piece over here. This is cold roll, and this is aluminum, or it was aluminum 6013. Again, this is the corrosion rate we had at the beginning, 230. And as the previous video showed, we reduced that from 4 to 2. Good. My boss is happy, everybody's happy. However, we quickly see that this part actually interacts with this one over here, with another one over here, and another bracket over here, which is this one over here. So this system has 4 different parts. If I do the same analysis of this component, in CFD, we're going to see a totally different story here. Remember, NX is just, again, 1-to-1, but it considers different anode-cathode ratio. But still, it doesn't take into consideration the gradients that we have here due to the different electrochemical signals. And gradients are important. Look what happened. The story is totally different. Now, after running my CFD, the same boundary conditions, the same conditions for the electrolyte thickness and all of that, I didn't change anything. We see that the aluminum 6013, the corrosion rate is actually 2,000 microns per year. Whereas NX mentioned or told me, hey, it's 230. That's perfectly fine. We know that the scope of these two technologies are different. That's perfectly fine. And also, I'm seeing corrosion rate on the 4130 over here, which NX, of course, tells me the same thing. We're using the same data. Okay, let's just resolve this problem. Because I know that NX doesn't have the capability to analyze these multiple different materials. It doesn't. Okay, let me repeat the same procedure I did on the second video with CFD. I change from 6013 to 2024, boom, no corrosion rate. And that's even better. But because it was 2, now I see that my corrosion risk is pretty much 0. Perfect. But now I have another problem. This was 300 microns per year, and now it increased to 1,000. That's perfectly fine because I changed the system. Now my system converged to a totally different equilibrium point. But that doesn't mean I cannot resolve that. Of course I can. And that's what we do here. Now that I have the information of my entire system, let me just see what happens if I change the material of this component over here. It was 4130, and since I have to be consistent because I don't want somebody from the mechanical team call me, Julio, why did you change from 4130 to aluminum? That doesn't make sense. Okay, let me just change that to 4340, which have similar mechanical properties. And what we see here is that we change, or we reduce the corrosion rate from this component from 1,000 microns per year to 120 microns per year. If I do the same process in NX, changing from this material to this material, of course, NX only takes into consideration the interaction between these two. It reduces to 86, which is great. It's definitely great. The point I want to make here is that we have to use the right tool at the right point of the engineering project. This is a quick recap because now we're switching gears to the Corrosion Toolset developed in Teamcenter. But here I just wanted to revisit a few important thoughts from the presentation. So anode-cathode ratio is important. Corrosion Gene considers that NX actually will have that capability in the 2604, but it is not in the production version that is actually ready in production. But it's important to understand that the NX is really, really, really good at, let's just rank and find the hotspots and focus on the hotspot. It's really, really efficient for that. And when we have multiple materials and different phase pairs, let's resolve that explicitly using CFD. NX takes seconds, and CFD, we all know that takes hours, days, and you need to be expert on meshing, pre-processing, all of that. And more importantly, let's resolve those issues early in the design process. That is really, really important. That is exactly what we hear from our customer. I wish I had this 4 or 5 years ago. I wish we knew this before. Well, now you have the tool. Now you have to simply get the license, and you can start using this. What about sustainability and maintenance? on the right side of the engineering process? Well, we developed something, like I said, that we call the Corrosion Toolset, because we believe that democratization of CFD tool is important for the corrosion space. Most of the time, corrosion experts are not CFD experts, and most of the time, they have no idea what CFD even means. So with that in mind, Siemens and Cordesa, we develop a set of templates. And we see here the templates that we have developed so far. M&P, operations, sustainment, maintenance, they can highly take advantage of this. Incredible. But we understand that you need expertise in CFD. And that is the reason why we said, okay, don't worry, we got you. We're going to make everything easy for you. We're going to script everything so that you just select a few simple things like geometry, thicknesses, and boom, you're going to have your CFD solution. And we reduce the complexity of systems using canonical geometries. This one is the C17, the fuel access door, and you're going to see why canonicals are important. We agree that you can represent different type of systems, complex system, in these different templates we have created. For example, over here we have fasteners, and of course now we have the interaction between this piece over here and this piece over here. So we can actually see that, well, this is a butt joint, and then I have a fastener with a lap joint bolted connection, and based on that we develop our library. So this is my computational representation of this piece over here, the same CAD, and this is what we call the model 2 that resolve the interaction between these two, and the model 1 that resolve the interaction between this piece, this whole piece, and this piece over here. Of course, the reason behind the canonical is, again, based on the type of equations we are solving that, numerically speaking, are elliptic, and because of that, we can actually make these assumptions. After using our templates, we assign the materials, dimensions, all of that inside Teamcenter. You will see that shortly. And we just click the button and we run. Look this. If we are right, if our assumption is right, then the corrosion rate I obtained from a full-blown 3D CFD simulation should be similar to the one that I get from my templates. And that's exactly what this picture shows. We see that the corrosion rate, the maximum corrosion rate on my aluminum 7075, which is this one over here, is somewhere around 300 microns per year. But my template, that is just a simplification of my model, predicts a corrosion rate of 320. It's absolutely amazing. And this took me more than a week. Pre-processing, meshing, blah, blah, blah. More than a week. And this takes 1 minute. And this is just amazing. That's the reason why folks at Air Force are so interested on deploying this solution pretty much nationwide. Here, the template over here basically is, I'm interested to see the interaction between the 7075 and the 7150, and that's what we have here. And again, the corrosion rate is somewhere around 40. If I'm not mistaken, I can see that clearly here, but somewhere around 40. But again, we know because of the galvanic series and all of that, that the important thing, or the important issue here is the titanium, the interaction between the titanium and the aluminum. This is the solution on Teamcenter, and you will clearly see that that's exactly the problem I just mentioned. We have that. Well, we have the version of work and active workspace, of course, but here you are going to see that we're going to we're going to launch Corrosion Gene, which is our database, the solution. We're going to select the materials that we need for this example. We are selecting here the environment, polarization curves over here. I just check a few things. I'm exporting that, and I'm selecting the other group. When I export that, Teamcenter takes care of everything for me. It moves the polarization curve to the scratch directory, and these are the templates I just mentioned. The user only requires to define the dimensions, because Teamcenter, like I say, it just manages the workflow, data management, and all of that, and this takes no more than 5 minutes. One important thing that we and our clients like is that imagine, for example, you have your own database or your own material, you bring that to Corrosion Gene, Teamcenter manages everything, that information propagates throughout the entire organization. You can have access almost at real time. There's no need for sticky notes. That's basically what I call, do you have this polarization curve? Or do you have this electrochemical property? Everything is in Teamcenter. Everything is managed by Teamcenter. And we have the ability to try and test multiple what-if scenarios. And one important thing is that if you need a specific template, we can develop that for you. And that's another interesting relationship we are building with Siemens, that we can develop tailored solutions for our customers. One of them is Northrop Grumman, that we recently worked together because they were interested in some specific geometries for their own application. Yes, we can definitely do that for you. Oh, we need new material in our database. Yes, we can definitely do that for you. And that's thanks to the really good relationship Cordesa has with Siemens. Conclusion, I definitely like to see these, use this example of a toolbox. As I mentioned, we cannot resolve everything with the hammer, even though it looks like easy that you can just use the hammer for everything. But definitely we need to use specific tools for a specific type of solutions. All tools are essential. Okay, so we see StarCCM Plus somewhere here. Teamcenter, of course, is my toolbox, and my corrosion gene data is somewhere here, and NX is somewhere here. We can develop. You need a new tool, like Hex, for example. Oh yeah, call us. We will develop that specific template for you. We are witnessing. That's something I like to repeat. We are witnessing the creation of a new computational discipline that we like to call it computational corrosion analysis. And we feel very proud for the work we are doing and how we are helping our customers. This toolbox is cost effective because, again, NX is really fast, licenses costs are different, time, expertise, all of that. And just grab your toolbox and start tightening those loose fastener early in the process. Basically, that's NX. You have your CAD, start working at the CAD level way before it's in the manufacturing line. And just leave those difficult problems for the experts. So I want to thank it's important to acknowledge the contribution from Siemens folks. I'm sure that I'm missing some names. We have been working together for pretty much like 3 years. And it is important to thank and acknowledge the contribution of our customer at Air Force, Dave Pett and Monali Patel. So thank you very much. If you have questions, cool. Yes, please.
So let's say I was with the Air Force and I'm flying or maintaining C-17 in the Indian Ocean, and I'm flying to Guam. And I go to Hawaii, but I just repeat that same loop over and over and over, and I'm in a different environmental condition. What do we do?
Yes, Bill, that's a great question. And I'm glad you brought that up. I'm sure you are aware of the D2P2. So we are currently working on that, and I appreciate you brought that up because I missed that part on the presentation. We're currently working on a project we call D2P2. We plan to deploy this for the Air Force Launchpad, and currently we're working on something called environmental severity indexes. And we are developing a new statistical method that will leverage APIs from weather data. We're going to bring that inside StarCCM Plus and take that into consideration to understand what happened under that scenario. So if you have this plane here, we pull the weather data, and we can actually build a history of that plane, and we can see what happened with the corrosion rate, because as Bill mentioned, environment is everything here. So once the plane is in Guam or California, whatever, the system reacts totally different. And we're working in that technology currently at this point. No? Well, thank you very much.